What is the unit? What is the difference? Now, the radius is also very similar to what? Yes or no? So how could you identify the difference? Yes or no? If someone were to ask, what's the difference between moment and a torque, right? I think I taught this briefly in 2Q, yes or no? Right? You'll be like scratching your head, okay? As I said, a prof in engineering physics really pissed me off. He says the same thing. It's not the same thing. Already spelling is different. One is M-O-M-E-M-T, the other one is T-O-R-Q-U-E. Are we clear? So they don't represent the same thing, okay? So with this, I'm going to show you an example how to identify the difference between a moment and a what? And a torque first, okay? Now, there are a few things that you need to know, and these are very important points because this is the last section in bending moment, and after that, we are going to do shearing stress, the worst topic that you can get in engineering mechanics, okay? Right. My suggestion is you write notes, don't copy what I put here, okay, but write some notes, okay? This is the structure you see. What you have is element H and element K, right? So you can identify where is element H and where is element K. What is an element in the real world? Does someone has a thick permanent marker? Thick permanent marker. No, I don't want those in segregate. I want to do better user. Oh. Very good. Now, what is an element over there? What if we have built this building and there's a crack? There's a crack someone or somewhere, okay? And we were told to measure the what? Measure the crack. I'm not sure if it's drawn by me. And I think it is. So how do you measure it? Right? So you get rid of everyone in the room and you're going to measure the stress. How are you going to measure it? You put what? Strain gauges. Or for example, now the weather is nice, no wind blowing. When the wind starts to blow, the structure is going to be problem. So what do? You put strain gauges looking like this. This is one strain gauge. In this short videoing of Professor Mechanism, McMaster, you said it. It's okay, I understand. I'm in more trouble than you can think of. So we know this will change, will measure the change in what? In Y direction. But because the building might be swaying left to right, we put another one. Strain gauge, and this will measure the change in what? Change in X. You know why I like this diagram? They have not a clue which professor drew it. Is it a mechanical or is it electrical? That will be pointing at the engineer. Yeah, so 7 is also I drew that. So if you see any of this, it's done by me. Are we clear? So we put strain gauges over there. Once we get the strain gauge, once we get the data from the strain gauge, what we do is we draw an element saying that what are the normal stress in the X, in the Y direction what are the normal stress in the X direction. Are we clear? Whenever you come here, you know what is an element. You look there, making. Are we clear? Okay. So those elements are there. We clear? Because sometimes you see, what is an element? How does it make sense? Does that make sense to you now? So next time, when you are engineers, which you all will be, you are asked to analyze a structure that has been loaded. You don't know the forces, but you can put what? Right. So from here, the elements, like what you see over there, are points of interest. Usually, all these elements, you position them where? At location where failure will what? Occur. You don't put them anywhere. Okay, if you put them anywhere, means you have no clue what you're doing. Okay, you put them where failure occurs. For this case, that's why sometimes for me to teach you guys is not easy from what the question is trying to ask you and what's happening in the real world. Can someone tell me where failure will occur? Yes. Yeah, to be in at the wall. The other position is at the elbow. Okay. So we're going to assume that it's going to occur at the wall, and you should put the strain gauge square. Okay. In this case, the question says the strain gauge is at that location. Evans, you clear about that? Good. Okay. Because Evans to put up his hand, this is right. So from here, this is what we have to do. Whenever you see anything like this is a 3D problem. Our paper is in 3D or 2D. We have to solve this problem in 2D. Then it can be done. Okay? Companies pay hundreds over thousands of dollars to buy software to analyze this. If you work in any company, you're going to pay 2D. Are we clear? That's the purpose of this one. Now, so what we do now is we're going to draw the transformation. I can, at the end of the day, I can give you any of this structure you can analyze, okay? So this is our transformation. So we follow the global transformation given in the diagram. Okay? So the first thing we do, we are going to analyze, okay? We are going to analyze on the XY plane. Now, can you all sketch how the XY plane look like? Just sketch, okay? So if I were to look at the XY plane, it will look like this. This is just a sketch. Agree or disagree? Then from there, I want you all to put in the elements. Okay. So I want you all to put, so this is your element what? Over here, this is your element H. Over here, this is your element what? Element K. Okay. These elements are your position of interest. At the element, we are going to sketch the centroid. I repeat again, we are going to sketch the centroid. This centroid is relative to the elements. I repeat again, you're going to sketch the centroid, and the centroid are relative to the what? To the element. Just a sketch for now. Okay. After that, you position the force vector. Okay. So we have over here 150. You have something coming in at 200. And then you have something over here going in, and you have something over in. This is 50, and this is 150. Okay. So if we were to draw our transformation, this will be our X, and this will be our Y. Okay. So the first rule, rule number 1. Ignore the cross and dots. Simple enough to understand? Yes or no? Ignore the what? The cross and the dots. So by looking at this view, there's only one view, there's only one force that's important. What is it? 150. Okay, so from here, we know that Px will be equal to what? 150, and it's going to be positive. It's going to induce tensile on element H and element K. Yes or no? Right? The formula to use over here now, right? The formula to use is now stress X is equal to Px over A. Now, we are going to apply what we have learned earlier. Okay. If you look at the 550 over here, is it parallel to the centroid or perpendicular to the centroid that we've just drawn? Parallel, yes or no? So for this case, when the applied force is what? Parallel to the centroid, the position is to the what? The centroid. So for this case, we know that there will be a moment in our Y. So moment in our Y is equal to what? 150 multiplied by what? Anyone? So this is equal to 1,500 pound-inch. Yes, and then we know that it's going to go in this direction. So this is your moment about, sorry, Z. So moment about Z, you have nailed it down, and this is what? Positive, and this is what? No. This is what? Compression. This is in what? Tensor. A lot of students make mistake. They will say what? This is error. Okay, this is wrong. A lot of students make mistake is why the distance is not to the what? Why is the distance not to the what? Element. Why is it going through the what? Centroid. Yes or no? So many times. Been teaching this course for 13 times now. So many times. Okay. A lot of times they just go to that. And I've been expert witness, same mistake made in industry. And someone explained to me, why is it towards the centroid and not towards the element? So, yes. Yeah, but to point H is also there's a perpendicular distance. Right? You compensate for the radius. Yes. Don't think too much about the moment. Think about the formula. You're right down there. I'm not saying that you're wrong, but focus on the formula. What compensates for the position? You know, maybe I'm crazy. Hold on. What compensate is this? Yes. You have stress X is equal to mz over IZZ multiplied by Y. This determines